Okay, Assalamualaikum and good day. So I will continue my lecture for chapter 4 part 2 on power quality. Okay, this is the content title for part 2. So there are 4.6 here for part 2 is about harmonics consideration, and 4.7 is about overview of other PQ issues, voltage set, voltage swells, transient, standard of PQ. Okay, this is the harmonics in power system. First, we have to know what is the definitions of harmonics. Okay, based on IEEE standard. Okay, a sinusoidal component of a periodic wave or quantity having a frequency that is an integral multiply of the fundamental frequency. Okay, definition which refer to French mathematician. Okay, for this mathematician, it means a periodic non-sinusoidal function of a fundamental frequency f may be expressed as the sum of sinusoidal functions of frequencies which are multiplies of the fundamental frequency. Okay, there are two types of harmonics in power system. The first one is voltage and the second one is current. And for harmonic classification, there are three classification. The first one is subharmonics, okay, which refer to FH less than F, integer or characteristics harmonics. FH is equal to N, F. And the third one is non-integer or non-characteristic harmonics, refer to FH more than F, and FH is not same with NF, where F is equal to fundamental frequency, FH is equal to harmonics frequency, and is referred to integer. Okay, this is the condition of the harmonic characteristic. Okay, for this condition, F is equal to 50 Hz. Okay, so for the first classification, subharmonics, which is FH is equal to FH is less than F. So this is the subharmonic condition. Okay, less than 50 Hz. Okay, this is the DC value. Okay, and then for the second classification, which is characteristic harmonics, FH is equal to F. So this is the second characteristic, okay, which is refer to characteristics harmonics. Okay, or FH is equal to NF. So this is the second order of harmonics. Okay, and the third classification is non-integer or non-characteristic. Okay, this condition is FH is not equal to NF. So FH is not equal to NF. So this is the third classification, non-harmonics characteristic. Okay, this is the sinusoidal voltage or current function. Okay, we have voltage function and also we have current function. Okay, so this is refer to this waveform. Okay, sine wave. Okay, this one is for current. Okay, And then this is referred to the magnitude of voltage, and this is the peak value of current. And we have theta here. Theta is referred to the angle between voltage and current waveform. And then we have T here. Okay, T refer to the period, okay, of the full wave of voltage and current, okay, which is equal to 2 pi divided by omega. That is T. Okay, omega is referred to the angular velocity, which is equal to 2 pi f. Okay, the presence of harmonic components in the normal sinusoidal waveform produce a periodic non-sinusoidal waveform. Okay, this is the Fourier series formula for voltage that have harmonics. Okay, and this is the waveform that we can see here. This sinusoidal waveform have some harmonics here. This harmonics and this harmonics. Okay, next, this is the waveform. Okay, we can see here this is the waveform for fundamental. We can see this is the sinusoidal waveform here, and this is the third harmonic. Okay, there are harmonic here. Okay, and this waveform, okay, represent the waveform of fundamental plus third harmonics here. Okay, this waveform have some harmonics. Okay, the Fourier series is simplified to express the periodic voltage waveform with fundamental frequency. Okay, this is the frequency, and this is the formula for voltage. Okay. Okay, where AK and BK are the coefficient of the individual harmonics components. Okay, this is the AK and BK, which is represent the coefficient of the individual harmonics component. Okay, harmonic measurement indices, individual harmonic distortion, IHD. The first one, and IHD is ratio between the root mean square RMS value of the individual harmonics and the RMS value of the fundamentals. Okay, IHD can be calculated by using this formula. Okay, equation 4.18. And the second one is total harmonic distortion, THD. THD is ratio between the RMS value of the harmonics and the RMS value of the fundamental. So THD can be calculated by using this formula, equation 4.19. Okay, next is the root of the sum of the squares RSS and the THD of the bus voltage. Okay, for this example, okay, the Z system is given this value. Okay, this is for R and this is for X. Okay, in ohms, and there are frequency here. There are two frequency for two harmonics order. Fifth order is 250, and for 7 order is 350, and this is the line magnitude given. Okay, this one, there are two line magnitude, and we have to measure what is the voltage. Okay, THD of the bus voltage. So first we have to know what is the R total and X total. Okay, R just directly taken from the value given. Okay, this for R. Okay, so 0.03. Okay, this is for R. And for X, we have to times the value with the frequency, 2 pi f 2 pi f L here. So given L value 30 microhenry, and there are two different frequency. Okay, 250 and 350. So put all the value in the frequency for frequency, and then we get the value of X. Okay, this one is from 2 pi f 30 micro. Okay, from this formula. So then we have to calculate what is the Z out. Okay, Z out is in magnitude, so just convert Rx to Z magnitude by using calculator, polar form, or you just direct calculate the Z by using Z total is equal to R X power of 2. Okay, by using this formula. So to get the Z total. Okay, then we know that the I line is given in the example. Okay, then we have to calculate what is the VH. Okay, V is equal to I Z. So put all the value and then we get the value of V. Okay, next is harmonic sources in electrical system. So many nonlinear loads drawing sinusoidal currents from electrical power system. Okay, this non-sinusoidal current pass through different impedance in the power system and produce voltage harmonics. And the voltage harmonics propagate in power system and affect all the power system components. Okay, this is the harmonic source in electrical system from fluorescent lighting. So we can see here the amount of harmonics number 3, 5, 7 and 9 are high. Okay, so for this order, okay, the value of harmonic is high. So we can see here this is the waveform. Okay, this is the waveform having the harmonics, and this is the value of the high harmonics. Okay, next is the harmonic from the adjustable speed drive, ASD. ASD are widely used to control the speed of AC motor nowadays compared to the application of belts and pulley in 1970s. Okay, we can see here there are harmonics here, and this is the waveform from the ASD, and we can see that the maximum is at 5th and 7th order of harmonics. Okay, this is source from the personal computer. We can see here the waveform. Okay, the current waveform from the personal computer, and from the waveform we can get the harmonics distortion spectrum. Okay, this one is from switching supply and TV, aircon, laser printers, and we can see here that odd order harmonics contribute to high value. Okay, you can see that odd order can contribute to high value of harmonics. Okay, next is from the electric furnace. We can see high power and high harmonics distortion device in power system produce non-integer current harmonics during melting process. Okay, 5th and 7th harmonics are produced from the electric furnace. Okay, next is the source from AC and DC converter. If the number of converter or inverter pulse is P, then the order of harmonics current in AC side will be NP plus 1. Okay, by using this formula. And we can see this is the waveform when having harmonics. Okay, next is the effect of harmonics. Okay, there are some of effect of harmonics. The first one is disturbance to electric and electronic device, higher losses, extra neutral current, improper working of metering device, resonance problem. Okay, first we go to disturbance to electric and electronic device effects. Okay. Harmonics cause disturbance in sensitive load (IPS) such as sensitive medical device, control circuit and computers. Okay, control circuit that work on I or V zero crossing a higher sensitivity to harmonics and may not work properly in the presence of harmonics. Okay, we can see from this waveform there are some harmonics here that can give this disturbance to electric and electronics device. Okay, second effect of harmonics is higher losses. Okay, P losses is equal to I square R. Okay, by using this formula. Okay, with the present of harmonics. Okay, by using this formula. Okay, and excessive losses and torque fluctuation also appear in electric motors in the presence of harmonics because harmonics yields core losses and torque fluctuations. Only the fundamental components yield average torque in motors. Okay, the next effect is extra neutral current IN. The presence of I harmonics, especially third harmonics in electrical power system, increase neutral currents. In three-phase four-wire system, in addition to the increasing size of neutral wire due to higher IN, it also can cause overloading of power feeders, transformers, voltage distortion and common mode noise. And typical PC power supply can be shown in this table. Okay, we can see here for current harmonics. Okay, there are neutral current value here. Okay, next effect is improper working of metering devices. Okay, the percent of current and voltage harmonics of more than 5% may lead to improper working of conventional metering devices that utilize induction watt-hour meters. Okay, the next effect is resonance problem. Okay, I and V harmonics when passing through the power system or any other loads may cause a resonant problems. Figure below shows a kind of resonance where the load has a resonant frequency close to the fifth harmonics. Okay, we can see there are some harmonics here that give resonance. Okay, here is the subtopic 4.7 which about voltage sets. So first we go to definition of the voltage set. Okay, voltage sets occur when the RMS voltage value decrease over a limited time period before it settles and return to its average value. And magnitude of the nominal voltage. Okay, for voltage set, here the voltage magnitude is around 0.1 pu to 0.9 pu. For interruption, the magnitude is less than 0.1 per unit. And for duration, for instantaneous, the duration is between 0.5 cycles to 30 cycles. And for momentary, the duration is 30 cycles to 30 cycles to 3 seconds. And for temporary, from 3 seconds to 1 minute. Okay, this is the example how the voltage set will occur. Okay, when there an accident happen, which for this picture we can see that the car crash the distribution pole and the fault occur. And when the fault occur, there are voltage set condition will be occurred. Okay, this is the diagram how the voltage set will occur. And as shown in the previous picture, when the car crash the distribution pole. Okay, here, at here, and there are fault occur here. And for this part, okay, there are momentary distribution, momentary interruption will happen here. Okay, the circuit will be open due to the fault occur. Okay, for this part, okay, there are voltage set happen. Okay, this is happen when the voltage is below than 90% of the nominal voltage. Okay, the two parallel feeders experience voltage sagging until the fault is clear. Okay, this is the voltage sag sources. Okay, any sudden increase in very big load will cause a voltage sag. Okay, this will happen due to motors, faults, any faults, or switching. Okay, so continue with voltage sag sources. During starting, motors typically draw 6 to 8 times more current of their rated running, and motors may start and stop frequently. The common cause of these sags in industrial facilities because they own their large motors. Okay, this is the motor example. Okay, here is the RMS voltage and current. We can see here when the motors start, okay, there are current was nearly 3000 RMS during starting motors. Very high current here during the starting motors, and voltage sag to about 220, okay, here volt from 277 volt due to the motor starting. Okay, here is the voltage sag example. Okay, a stiff 14.4 kV 3-phase system serves a distribution line with an Z of 1.2 plus J6 ohms. If the volt at the sending end remains 14.4 kV, what is the V drop in the line due to a balanced 3-phase load of 10 plus J5 ohm per phase? Okay, given variables is Z load. Okay, this is for Z load given in the example, and also Z line, and also V phase. We have to divide by square root 3, okay, to get the V phase. And then we have to measure what is the line current. Okay, I line is equal to, by using current divider rules, okay, V phase divided by Z total plus Z line. So by using this formula, we get this I line. Okay, next, by using the line current, we have to find the voltage drop, okay, voltage drop, and also the load voltage before we get the percentage of voltage sag. So by using this formula, okay, we get the value of voltage drop. Okay, and then we have to calculate what is the V load. V load is equal to V phase or V system minus V drop, and then we get this value. Then we can calculate what is the voltage sag percentage by using this formula. Okay, put all the value in this formula. Okay, V phase, okay, we have V phase here, and then we have V load here, magnitude, and also divide by V phase, and then we get the percentage of voltage sag. Okay, this is the typical V sag tolerance based on IEEE 1346. Okay, there are some equipment here, okay, listed here, and also there are upper range here, and average range, and also for lower range. Okay, next is about transients. Okay, what is transient? Okay, electrical transients are momentary bursts of energy induced upon power data or communication lines. They are categorized by extremely high voltage that drive tremendous amount of current into an electrical circuit for a few millions up to few thousands of seconds. So from this diagram, you can see there are two types of transient. The first one is the impulsive transient, okay, very high transient here, and then we have oscillatory transient here. Okay, next is about types of transient. Okay, there are two. As we know, there are two types of transient. The first one is impulsive and the second one is oscillatory. So first we go to impulsive. Impulsive is having a nanosecond, okay, 5 nanosecond rise lasts below than 50 nanosecond. For microsecond, the duration is about 1 microsecond rise and lasts between 50 nanosecond to 1 millisecond. For millisecond, there are 1.5 millisecond rise up to 1 millisecond. Okay, the cause of the impulsive is by lightning, removal of an inductive load, loose wiring, and other arcing event. Okay, for oscillatory transients, okay, there are three types. The first type is low frequency. Okay, for low frequency, which below than 5 kilohertz. Okay, the duration is 0.3 to 50 millisecond. Okay, and then this is caused by capacitor switching, ferroresonance, and transformer energization. Okay, for medium frequency, okay, we have frequency from 5 to 500 kilohertz, and the duration is 20 microsecond. Okay, this is caused by back-to-back capacitor switching, cable switching, and impulse response. And the last one is high frequency, between 0.5 to 5 megahertz. Okay, the duration is 5 microsecond. Okay, and this is caused from the response of systems to an impulsive transient. Okay, next slide is about transient impact on loads. Okay, first one is hard disk crash. Okay, and then power supply failure. Okay, transient will give component failure, and then SCR failure, circuit board failures, process interruptions, and letting the smoke out. Okay, this is the transient sources. Okay, distribution system. For distribution system, there are source from lightnings, switching operation, circuit breaker, capacitors, and so on. And fault clearing or breaker operation. Okay, for customer system, the source of the transient is from the lightning. Okay, and then from arcing devices, starting and stop motors, breakers operation, and also capacitor switching. Okay, this is the illustration of transient sources from the lightning. We can see here from the cloud, okay, there are positive and negative charge. Okay, the negative charge will flow to the ground. Okay, attract with the positive charge at the ground. So this condition will give high frequency. Okay, this is the transient source due to fault. Okay, when fault occur, the voltage will drop here. Okay, will drop for certain value. This is due to the interruption of fault. And then there are occur over voltage transient here. This one is over voltage transient due to fault current interruption accompanied by oscillations at the natural frequency formed by L and C. Okay, this occur at the low frequency condition. Okay, this is the source due to motor starting. As we can see here, when motor is to start, so there are some transient happen here. Okay, for very high voltage, for very short period. So this will occur at the high frequency. Okay, this is the transient source due to capacitor bank switching. Okay, and when the capacitor start to switch, okay, there are some transient here for certain period, for certain duration at the low frequency before the voltage turns to the normal condition. This slide is about PQ standard. So there are two standards that we have to refer for PQ, power quality. The first one is IEEE, okay, Institute of Electrical Electronic Engineers, and the second one is IEC, International Electrotechnical Commission. So to meet all the standard of PQ, we have to refer to these two standard. Okay, here is the IEEE standard. Okay, for PQ, we can see here for transient and short duration variation. Okay, and then we have long duration variation and waveform distortion, voltage fluctuation, and also power frequency variation. So all the categories have their own standard. Okay, this is for IEC standard. Okay, there are categories, some categories here for over voltage transient. Okay, and then we have short duration voltage. Okay, and then we have long duration voltage, voltage waveform distortion, and also voltage fluctuation. So there are some typical characteristics that we have to meet this standard. Okay, that's all for chapter 4. Hope you enjoy this video. Okay, thank you.